Okay, so now the question is, what do we want to do with the results so that they can learn as they go on? Have this equation that is essentially a probability based on two factors that multiply. The first factor is something like 1 over the distance, like what we have, this like desirability based on proximity, which we're currently using as the weight. So we have that as this graph property weight. It's 1 over the distance. And then the other term is the pheromones, which we do not have yet. But we can initialize the pheromone to be constant on every edge. We can just go ahead and do this. Pheromone in it, make that a float, and we'll default it to (10e to the negative 6), and I'm taking that right out of this book. So every edge will start out with the same default value. We can change that if we want, but for now we'll leave it as the default. And then I will show you the equation. Let's see. Okay, pheromone. Let's see here. I'm actually eventually going to create a new class that encapsulates this logic, because there are a lot of different iterations of this algorithm and its details, and it would be nice to be able to kind of swap them in and out. So I'm going to write this as a function right now, update pheromone, but eventually I want to encapsulate that into a class, because we'll have multiple versions of this function. Right now I'll just do a simple one. Okay. Let me just write in the comments here. So T, I, J, T, or tau rather, tau ij, so that's basically the pheromone amount on edge ij at time t is going to be 1 minus rho times tau ij. Okay. So the next time will be the current one minus this evaporation, basically. So let's see. Rho actually, sorry, I'm going to put this at the end so that I can add a default argument. So let's say this is 0.5. So it will cut the pheromone in half from the previous time period and then add to it oh boy, I think I have the complicated one. Hold on a second. Okay. Plus delta tau ij at t. Okay, so basically we evaporate some of what was there and then we add to it the new stuff. So how do you get the new stuff? Okay, delta tau ij is, it's like all this nested stuff. Okay. Sum from k to m. So this is sum over the ants. Now how can I write? Q over LK. So Q is some constant, and then LK is the length of the path traversed by the ant. And this is only on the edges that are part of that path, of course. So I don't, maybe I'll write that like this. So some indicator ij is in tk, where t is the path of k, tk is the path of ant k. That's not exactly the notation in the book, but I can't do this fancy text formatting. Okay. I think that's all we need. Now we just need to implement this equation. So let's think about this. We have our model, which has our agents in it, right? And each agent, what is this? Get rid of this. Each agent has the cities visited and the traveled distance. So let's get rid of that. LK is the traveled distance. Q, we need Q. Q is 100. I'll put it after row. Well, alphabetically it comes first. Okay. So for agent, for ant, and Am I not getting my... Okay, what is it called? Oh, actually, this might be a nice method in the ants. Like some method like to calculate this. Well, it would be the K, this for ant K, and then we sum it over the ants to get this total quantity. Yeah, well, let's do that. Because we'll eventually have to modify this decide next city to not only consider this distance, but also to consider the pheromone. So I think it makes sense to have a method at the ant level to return this value. Calculate pheromone delta. What else do we need here? We need is it just Q? And that can actually just be factored out, right? I could just as easily write this as Q times 1 over LK. Okay. I don't know. It doesn't really matter whether I pass it in or not. For consistency, I suppose I will. Okay, another nice thing is that the node IDs in this graph are just equal to the integers of the cities, which my cities visited list will simply be okay. So something like for I in, now let's see, how should we do this? How should I loop over this intelligently? My cities visited to get all the edges. So the first traversal is from the first element to the second element, and then from the second element to the third element. So I guess I should do their start city in self.cities visited -1 and city Where's Copilot in all of this? let's see. What data structure should I hold here? So each ant is going to return something at the edge level. If I had a dictionary for every ant, where the key was the tuple of nodes, the source and destination nodes, and the value was this thing, then for each edge in the graph, I could check every one of those dictionaries and add the values. That seems inefficient. The other thing I could do is have a single dictionary where each ant returns, and then I update it so that if there's a new element, I simply add it in, but if the element already exists, then I add to it. And then once I do that for all the ants, then I only have the edges that need that have this term in it, and then I could loop through and add it too. So I would basically have this. But I'm going to have to loop through every edge anyway to apply this part of the formula, because every edge has this decay. So maybe I just loop through the edges, I apply this, and then I loop over all of the ants to get this. I think that makes sense. I don't know. I think I'm going to just go with the way this is working so far. And if I have problems with it, I'll improve it. Okay. So, results, tuple, start city, end city. Equals 1 divided by self dot travel distance. I'm sorry, Q divided by self dot travel distance. Return results. Okay. I once again forget how to iterate over the ants. schedule. Okay, for agent and self.schedule agents. Delta tau J equals dictionary. Okay, for agent in model let's see. Equals agent dot, what do we call it? Calculate pheromone delta. Q. And VS Code is not helping me out much here. Copilot stopped working and it isn't finding these methods. Okay, so now I have a dictionary that's keyed by the agent number, I guess. I should probably use the ID here because I think they do have unique IDs. I don't think it really matters in this case because we're going to just throw it away. Okay, so now we should have this term, this Q divided by LK, but only for the edges that existed because we only looped through the cities in the city visited. Where did that go? Yeah, so we're only looking at edges that are part of the actual traversal path. And then we make them all 1 over the travel distance. So now we need to loop over all the edges in the graph, apply this, and then loop over each of the agents and sum up their terms for that edge. Okay. And graph edges. How can I get the properties out of this thing though? Loop over edges. Oops. Is my internet down? Is that the problem? Okay, apparently I don't have internet. That explains why Copilot's not working. Loop over edges. No internet. Okay. This video is really testing me. think the easiest thing to do would be to just get a graph, then I can play with it. So change. Okay. Oh, wait. I forgot that I was also returning the positions here. Okay. Oh, man. Okay, so that at least works getting the source and destination. Now, how do I get the... So graph, okay, I can just do it this way. But we called it something different, right? The existing amount of pheromone. Graph UV pheromone, okay. Here, we'll make this easier with our notation. Tau ij. What am I doing? Okay, tau ij at time t is what is currently there, right? Now, we want delta tau ij. So we just got this. Now we need this. So we need to loop over all of the ants and see if it has this term in it. So for k delta tau ij and delta tau ij dot items, whoops. Okay, so I want to basically loop over this thing where here's my key, here's my value. I don't actually care about the key, I don't think, in this case. Let's see, delta tau. So I want that won't exist in many cases, so we can default it to 0 like this. All right, so this extracts it from the ant. Okay, I'm trying to figure out how to name this stuff without it getting too confusing. So this is going to be the new thing. So we want 1 minus rho, right? 1 minus rho times the old thing. And that's stored in the graph. And to that, we want to add the ant things. So tau ij plus equals the value from the ants. And if it's not in that dictionary, we'll just add 0 to it, which does nothing. And then we can overwrite okay. Now how do we set it? So I guess I can extract it this way, but I don't know how to set the property. But how did we do it before? Yeah, it did not complain when we did it before. G, oops. Oh, I forgot this part. Okay. So this adds the ant's contribution. This evaporates. All right, well, let's see what happens. So we have our graph. We run iteration, and that does nothing. Then we need to call graph equals update pheromone. Well, I'll do that stuff first. And then graph equals update pheromone. I'm going to leave these default parameters. Okay. Now, this won't actually change what the ants do yet, but we'll see if we get any runtime errors. Okay, apparently not. Now, one thing I want to do is just, as an example, to see if the pheromone is changing, print out the pheromone level on a single edge. Pheromone equals graph 0, 1, let's say. Pheromone. Alright, so hopefully this changes with time. Alright, it starts off at 1e negative 5, and I think that's what we started at. Yeah, I'm sorry, I mistakenly wrote that as 10e negative 6. So it should start that way, right? Okay, so it starts out with the initial value. It starts decaying very quickly because it has this exponential decay of being cut in half every time, unless it's reinforced. And it doesn't look like that path is reinforced. Okay, so one path that is 0 to 8. Do we see that consistently? All right, so let's look at that path. Since this is in the best path, we should see that one getting better, I think. Yeah, okay. So now instead of decaying rapidly, it's getting a larger value. Awesome. Now, one last change we can make before concluding this rather long and painful experience is change this function. So the equation is quite simple. Okay, I was debating whether I create a new method or overwrite this one. I'm going to overwrite this one. We can always set the hyperparameters to recover the same behavior because the hyperparameters weight how much we leverage this distance versus the pheromone trail. And by setting the appropriate hyperparameter, we can totally eliminate the pheromone trail part, and it should be identical to what we have here. Okay, so we have our graph. Let me go ahead and write the equation. Okay, so we have our graph. We have the current city, neighbors. All right, yeah, we'll probably have to change the way this logic flows. I'm going to start down here and then copy paste things down and then erase. Okay, the equation. Pij. So the probability of going on ij is equal to 1 over z, where that'll be my partition where I'm just summing over all possibilities. Tau ij raised to the alpha times one over distance raised to the beta. And that is it. So I guess the thing to do is to calculate this for every possible edge, because the only ones possible are the ones starting in my current city and ending in a city I have not yet visited. So I need to calculate this quantity for each of those and then normalize by adding those all together and calling that z. Okay, so current city is I. I'm going to keep neighbors. Now this is where we'll start getting a difference. Okay, Neighbors not visited. Neighbors not visited. Maybe we'll call that candidates. For city and candidates, all right, we're going to need alpha float. Let me see the values. 1 for alpha, 5 for beta. Okay. For city and candidates. So we have G, right? From current city to city. Pheromone. Is that what it's called? Times, let's see, did we get the distance? No. 1 divided by I think that they call this visibility. I'm just going to call it the same thing, visibility. Wait. Okay. Okay, so here we have the quantity. Let's do this. It's important. By okay. Results.sum is our partition, and results Okay. So we should now have probabilities. So now I just need to pick one of these choices using these as weights. And of course I would look up how to do that in NumPy because I forget, but I don't have internet right now. So I'm gonna guess what it is. MP dot, or wait, model dot random dot choice. I have a model here, right? Or self dot model. Dot random dot choice. Range, oh wait, candidates where weights equals results. Let's see. Let me go ahead and try to play with this. Alright, don't complain about that. Cities equals 20. Okay. Okay. We have that. What was that? Oops. Okay, now I have a model. Model that random dot choice. Say A, B, C. Weights equals 0.9, 0.09, 0.01. Does this work? How can I look at the documentation without the internet? Maybe it's just weight. Oh, this isn't NumPy either. I think it's just the random library. I don't know, let's see if we can find it this way. Nope, sorry. choices. Return a k-size list of population elements chosen with replacement. I think I'm okay with that because I only want one anyway. Choices, population, weights. Okay. I think this is going to be it. Okay. Little trial and error. Random choices. Candidates. Return new city. Oh, we did have this edge case. Length candidates is 0. Return none. What do we do? If new city is none, return current city. Okay, I think we can delete all this. This just found, travel distance. We need to do that. New city, distance. Okay. Cool. Let's see if this works. Okay, apparently either current city or new city is a list. Oh. That's because this returns a list. Wow, this seems to be working. $3.705. All right, I think we have implemented the algorithm. There, of course, is probably bugs. We'll find them when we start collecting data and doing this correctly, robustly. But I think as a first pass, let's do 1,000 episodes, see what happens. So how quickly did it find this path? It's like a reasonably tight distribution here. Okay, so the best distance it found was like 15% of the way in. 3.74, what was this? 3.70 or 71. Okay, wow, okay. It seems like, at least at first pass, it's behaving reasonably. I think I'm going to wrap it up here. This is already a long video. And after this, we can start collecting data and seeing if things make sense and changing hyperparameters and so on. So if you stuck through, congratulations. It was a tough one.